Hello everyone, this is Star, and I'm recording this video for a makeup for the course tutor section week 7 for CS61B fall 2019. And in this section, we're going to talk about two things. One is asymptotic runtime analysis, and the other one is number representation. So now let's start with asymptotic runtime. So first, there is a couple of key ideas that we need to take away. So first, given any Java function, or actually any function in any kind of programming language, there will be arguments, and all the arguments will have a size, which is for us to decide what is the size. And then, for example, there can be a couple of examples of the argument. For example, a size can be the value of an integer, or it can be the length of a list or a string, and so on and so forth. And sometimes we do have multiple variables. We can either have multiple inputs, or it's possible that our input is a matrix by itself and thus will have multiple dimensions, which is why we have multiple sizes. And after we know what is the size, we can jump into how to describe a runtime in regard of the input size. And first, we cannot do analysis on the runtime without a input size. So it is very important for us to assign variables to describe the input size first. And after that, we're going to give a function that describes a runtime. So basically, what does runtime mean is a runtime is just a function with respect to the input variables. And thus, it is a function that describes how our function is going to behave in regards of the input sizes. And in this class, we use this big O, theta, and omega notation, which I put a bunch of words in here, but the key point here is, so for big O, it is used to describing the upper bound for a runtime, and big omega is for the lower bound, and the big theta is for the tight bound. And remember, a big theta is only defined if the big O and the big omega give you the same bound, which means the bound coincide with each other. And remember, since we're doing analysis, there is a couple of sequences that you may find really useful in this class, or when you're doing runtime analysis. So the first one is for a sequence that's starting from 1, 2, 3, 4, all the way to n, and for each number here, they have the same difference between each other. And in this kind of sequence, you can do some really basic and for this kind of sequence, you can do some algebra and figure out the sum can be expressed in the sense that it's n squared. And the other one that is 1, 2, 4, 8, 16, or for every term in the sequence, they have the same ratio with respect to each other. And in this case, the sum can be expressed in theta n. And one thing that is really important besides this is in runtime analysis, we do not care about the constant. So for example, when we are talking about a time constant, we are talking about a runtime that is theta n, it is asymptotic the same as theta 3n because constant does not matter. However, what does matter is when the constant is in exponential term. So for example, theta squared will not be the same as theta cube, or theta n squared will not be the same as theta n cube. And for example, theta n cube is definitely not the same as theta n to the 100. So there is a couple of rules that we want to remember for the order of growth. And here is a quick summary of it. This is something that you may encounter very often when you are doing runtime analysis. So starting from the first one, which is the fastest runtime, to the last one, which is the slowest runtime that we may usually encounter. So the first one is a constant, and then we have log, which is a logarithm runtime, and then we have linear, and then we have a linear times logarithm. And remember, since this logarithm term have the variable n, which is the input size in there, so we cannot ignore it. All right, and there is polynomials, and there is exponentials. And the difference between polynomial and exponential is that for polynomial, our input size variable n is serving as the base, versus in the exponential term, our input size n is served as the exponential number, which is k to the n, where k can be any arbitrary constant. And then we have factorial, and finally we have n to the n, which is pretty much a runtime that you do not want to design your algorithm to be, because it's really, really slow and hard to deal with. And this is just something you're going to meet a lot in your life or when you are designing programs either for interviews or for your daily practice. And yeah, a better runtime typically means you are able to run this code theoretically in a faster way. However, there is other factors that is affecting your speed or the code, how fast your code is running, such as the hardware or like other things that you may be able to know when you take CS 620 or 162 that can help you to understand how to make everything faster besides a better runtime algorithm.